Welcome to the Rare Earth Elements podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the Jackson School of Geosciences at the University of Texas at Austin. In this podcast, we discuss rare earth element feedstocks with experts from academia, industry, and government. The discussions include a variety of potential feedstocks, particularly waste materials, and innovations in processing technologies to improve rare earth element supply chains in the US. I'm pleased to welcome Davin Bagdonas to the podcast. Davin is a senior research professional at the Center for Economic Geology Research at the University of Wyoming. And his research focuses a lot recently on rare earth elements, and particularly in coal and other materials. And we first started collaborating a few years ago through a Department of Energy Core CM project, Carbon Ore Rare Earth Critical Mineral Project. Thank you so much, Davin, for taking part in the podcast.
Thank you, Bridget, for having me. It's a pleasure to continue collaborating with you this time on a podcast.
So, Davin, Wyoming has been in the news a lot recently about the Brook mine and the rare earth element potential in that mine. And I think Secretary Wright was talking to the media about the potential for rare earth element production. I saw an older article from the Wall Street Journal talking about 2 million coal mine that might hold a 37 billion treasure. So maybe you can tell us a little bit about the Brook mine and what the resources look like.
Yeah, I can say some things. I haven't directly partnered with the Brook operation, but a lot of the preliminary work that went into that site was done by a colleague at NETL, and it was one of the sites that helped us develop new methods for assessing critical minerals, rare earth elements especially, in coal sediment systems. So it was one of the test sites, some of the core, realizing that in fact, some of these critical mineral occurrences in coal sediment systems are now a recognizable or describable ore body of sorts. So it was a critical piece of the puzzle there. Having worked across Powder River Basin of Wyoming, where the Brook mine is, looking at a number of sites there, it is an interesting basin, and it is I would say, a unique coal in terms of not only the critical minerals occurrence with rare earth elements, but where they occur in the coal and some of the major oxides, things like calcium, that seem to be anomalous there too. So it's somewhat of a unique geologic system.
Right, and I was just looking at different reports about it and seeing they mentioned maybe about 1.5 million tons of rare earths with about 500 parts per million total rare earths on an ash basis. And also seeing 65% of the critical mineral oxides, ranging from 300 to 400 parts per million. So that's a pretty large resource, considering that we use US uses about 8,000 tons of rare earth oxides annually. And I guess, some of the reports were talking about China having restrictions on exports. We're so dependent on China for rare earths, and then they imposed restrictions in April of 7 different rare earth elements, including some that are used for permanent magnets, dysprosium, terbium, and also very important ones like scandium and yttrium. And I think I also saw mention of other elements in addition to the rare earths, gallium and germanium, and having quite sizable fractions of those. Any thoughts on the range of rare earth elements?
Yeah, I think it's important to not only talk about the range, but the occurrence of the individual species or the ratio of the rare earths in not only the Brook, but other Powder River Basin mines that we've researched to date over the past several years. When you look at the occurrence of rare earth elements in these coal systems in the Powder River Basin, it's noticeable that the middle to heavy rare earths are fairly enriched. If we use a traditional metric of looking at critical rare earths, those are mostly middle to heavy rare earths compared to the lights, you're looking around 35%, 36% on average to numbers all the way up into 60, 70%. Comparing that to a traditional rare earth mine like Mountain Pass, those traditional deposits tend to be heavily enriched in light rare earths. We often call those excess rare earths because they're lower value. They're produced in such high numbers in traditional rare earth ore bodies that although you're paying to extract them through the whole process, you're paying to produce things of low value. So it's a net loss, or at least dinging your overall your overhead of the operation. In the coals like the Brooks and the others in the PRB, those lighter elements, those lighter rare earths are less concentrated. Things like germanium, gallium, I'll add antimony to the argument here, co-occur. That's not always the case in coals, but if we start to consider not just rare earths, but other critical minerals, it becomes a very interesting deposit. And again, not just the Brook, but all across the Powder River Basin. Again, it appears to be a fairly unique coal system in terms of critical minerals occurrence.
Right, and the work that you did with Scott Montrose at NETL on the Brook, using the Brook data as an example, you guys developed a model for where a conceptual model of how the rare earths might become concentrated at the margins of the coal seams. And coming up from beneath. Could you describe that a little bit, Davin?
Yeah, and Scott's a valued colleague. We've brainstormed a lot over the years in the coal science part of this. I will caution, neither of us is a coal scientist, so this has been an interesting process. Backgrounds in igneous systems, igneous geology. But I think, knowing that's where traditional ore bodies occur, generally for rare earths, taking that knowledge into coal systems was a big step. So the methodology we had kind of developed and worked on, the Brook mine was one of those sites. Scott has much more experience there than I do. I was working at other coal mines using similar methods, developing similar methods. We were starting to see the same thing on the boundaries of these coal seams. So the very top and the very bottom, we were starting to see significant concentrations of the rare earth elements. So we've loosely coined that a bounding enrichment. Previous authors had referred to it as the near coal boundary. So it's not a completely new finding, but it's new in terms of defining an ore body now in a coal sediment system, which hadn't been done before. So those bounding enrichments are certainly where the geochemical activity is taking place, the sortation of the rare earth elements, the concentration of metals. The big activity seems to be right on the edge of the coal seam.
Right, and the Powder River Basin is a really famous coal production area in the U.S. I think it accounts for about 40% of U.S. coal production, and then you export it all over the U.S. to different power plants. And it's known for, the coal in the Powder River Basin is known for having low ash content. You mentioned earlier 5% or so or less. And so when you present the rare earth element, when people present the rare earth element concentrations on an ash basis, then on a coal basis, then they might be much lower if the ash fraction is so low. So I guess if we had 100 parts per million rare earth elements, total rare earth elements, and we had 10% ash. So if you present that, if the 100 parts per million is on an ash basis, then that would be 10 parts per million on a whole rock basis. And I guess it also depends how they extract the rare earths. I mean, if you burn coal, and like you've done a lot of work on coal ash, the coal ash that's left behind, then the rare earths concentrate in that. So then it seems appropriate then to talk about it on an ash basis.
And those are really important points for all of us working in critical minerals and coal space. Unfortunately, not everyone presents data as an ash basis or a coal basis number. Sometimes it's hard to determine what that overall concentration is that they're presenting. But you're right. The example of a 100 ppm ash number for a 10% ash is actually a 10 ppm geologic material. So if we're comparing the coal to a granite or any other lithology, apples to apples, we would want to take our numbers and put them in a coal basis value set. But the reason we ash the material, there's a couple of reasons. One, the methods for assessing trace elements in coal. If you have like a Powder River Basin coal where 5% of that coal is the mineral content, 95% is carbon and oxygen and those things in the coal molecule, you can't directly analyze that through ICP methods, modern state-of-the-art methods. So we have to ash it first. That's a USGS standard procedure. And we end up with this leftover mineral content in the ash, which we analyze through ICP. It also provides us a pathway to better compare directly the mineral content itself. So if we're comparing where the rare earths occur in the mineral content of a coal, we can take that number and compare it to a traditional ore body where, again, the rare earths are occurring within mineral phases. And it's also directly comparable to power station waste where, through the thermal production process, you're creating an ash. But it's a cautionary tale. When we present data for these coals, and some concentrations we see in the peer review are 4,000 and 5,000 ppm total rare earths, you have to also, in that spreadsheet, have an ash percent for each of those samples so we can back calculate. Extraction does matter. There are a lot of things we can do with coal and the coal molecule, where if we have a 5% ash coal, 95% still is usable. So co-production, we may be able to produce a carbon-based material, generate a waste stream, and then that concentration, that 5% mineral content, becomes your extractable waste stream for the rare earths. So it has meaning, but we have to be careful in how we talk about it and how we report.
And you're right. I mean, when I was talking to Nolan Thaker about the coals in the Williston Basin, so it seemed like they're planning on extracting the rare earths directly from the coal because the rare earths are associated with the organic phase in the coal there. And so presenting the numbers on a whole rock basis or a coal basis seems appropriate there. And it just depends how they will extract the rare earths from the Powder River Basin, and if they're at the margins of the coal seam, is there, how much clay or how much of other mineral material are they associated with the organics, or are they associated with the mineral fraction? Do you think these are like the lignites, or do you think these are, this is different? This is subbituminous coal, so it's the rare earths are associated with the mineral phase. Is that correct?
It's a really good question, and I'll take one step back. When we look at these resources, and this is a really important note you made me think of, it's not just concentration. It's the volume of accessible critical mineral, in this case, rare earths, and the extractability. What mineral phase are they in? The North Dakota example is a good one. These are bound organically, for the most part, to a lignite. Therefore, they're very easily extracted. It's a feasibly economic process. So in the Powder River Basin, our coals are not that great. If you want to burn it for power station use, they're fantastic, but they're not a high-grade coal. They're a subbituminous C, and we do see coals I would describe as a lignite. So we think, we've done some preliminary testing, we think the rare earths are bound in a multi-phase group in those boundaries. So certainly organic contribution there. There are some low-temperature authigenic phosphatic minerals, and then there are probably some sorbed clays and other related things. So the rare earths are not existing in refractory minerals for the most part. at least in the majority of PRB materials we see. So in theory, extractability should be fairly easy. Some preliminary tests with weak acids have shown mobilization directly from the coal. The School of Energy Resources, where I'm located, also has processes they're working on upscaling to demonstration where we manipulate the carbon and oxygen, the coal molecules themselves for other things, building materials, carbon materials, and then we have the leftover for rare earth extraction. So some of those processes to liberate the carbon actually benefit the rare earth extraction. So in terms of concentration, not that great, but volume and extractability are pretty positive.
Right. And you also mentioned having other critical minerals like gallium and germanium and others. And I know Department of Defense is very interested, I think, in gallium and scandium. And so having those also is a real plus. So you have also worked on the Green River and Wind River basins, those coals, as part of the Department of Energy Carbon Ore Rare Earth Critical Mineral Project. Maybe you can describe those resources, Davin.
Yeah, that's a great comparison. I was the principal investigator for the Green River Basin, Wind River Basin Consortium Phase 1. That was one of two projects we had at the University of Wyoming. It provided a great contrast to Powder River Basin coals. Powder River Basin coals being a terrestrial closed basin system. The Green River Basin coals are a marine system. Very different coals. They completely lack calcium. They're a little bit higher grade bituminous coals for the most part. They're older. A lot have undergone significant events in the life of the coal through laramide orogenic events in the basin building. There's faults. A lot of the coal seams are separated with large non-coal sediment packages. So sandstones, shales, things that can or cannot contribute to fluids, water, minerals, elements traversing the system and being deposited. There were a lot of lessons learned. Some of the grids we did to sample Green River Basin coals that we took from Powder River Basin didn't really work at first. We weren't finding interesting occurrences of rare earth elements. And I'm glad you brought up germanium and gallium. One of the lessons learned, the critical minerals list does change, and emphasis on different elements is frustratingly quick sometimes. So we weren't actually looking for germanium and gallium in a lot of samples early on, or lithium or other things like that. Luckily, we were able to resample a lot of locations in Green River Basin, and we started to notice these elements, critical minerals, occur in the near coal boundary, the boundary enrichment, but rather than in the coal itself, like the PRB, we see them in the non-coal sediment, so carb, shale, clay-rich portions immediately adjacent to the coal. So presumably the coal is still serving as a bit of a filter, an pH boundary, but we're seeing the activity for the mineral host more so in the clays than the coals themselves. And there's probably some differences there in coal grade, overall chemistry, hostability. There's a lot of factors there. Interestingly, a lot of the time the rare earths are not the most interesting in Green River Basin. We found cobalt, nickel, chromium, lithium, things like that, iron in iron-rich phases, and then in the clay species as well. So a little bit different animal there. It took us a lot of time to figure that one out, actually.
And what sort of levels of total rare earths were you finding in the samples there in the Green River or Wind River?
That's a great question. We did see 600 all the way up to 1,800 ppm total rare earths. Those were in higher ash materials a lot of the time. So if we're looking at a clay, that may be a 60% ash number, which is quite different than Powder River Basin. And then some just don't have an ash number. Some were just true clay samples, especially where we found some lithium There were pyritic horizons. So we have iron sulfide species that had quite a bit of nickel, for example. So a pretty different system and different concentrations, but also a different ash percentage. Another reason to attach that ash percent to our data.
And you mentioned earlier in the Brook mine that you may have 40% to 60% heavy rare earth elements. What was it like in these other basins, the Green River or Wind River?
For rare earth elements, we had what I would call a more traditional ratio. We were richer on the lights. That being said, some of the testing our friends at Colorado School of Mines had done on the pyrite-rich coals did find good extraction of neodymium. I want to say dysprosium, and then they had nickel and cobalt come out of those pyrites as well. So they weren't the best in terms of ratio for heavies for like Department of Defense use, but in terms of some of the energy rare earths and some of the co-produced other metals of interest, it was a good result.
And, reading the paper that you co-authored with Scott Montrose and the Brook mine being one of the examples, and in the recent literature, they're saying, 1.5 million tons of rare earths. So they have a geologic model then to estimate and to interpolate and extrapolate from the samples and stuff. And you mentioned in the Green River and Wind River that, it's an older coals and there's a lot of faulting and others. So it would probably be much more difficult to estimate the rare earth element reserves there, even if there's more interest in other things, but just because it's geologically more complex. Can you describe a little bit the geologic model that they used at the Brook mine, or the methodology that they used to develop the reserve estimates?
Yeah, so I don't actually know the exact step-by-step methodology they adopted, but it is a greenfield or was a greenfield site, meaning it hadn't been previously explored for rare earth elements as an ore body. So typically you'll go in, begin to recognize through selective sampling locations of interest. And as you get geochemical data back, you start to gain an understanding of extent and occurrence, which coal seams are more interesting, and essentially apply a grid. So the methods we utilize, you start to pull coal core and incrementally sample the core, first in a larger grid, both in depth and across the mine site, and then in more refined intervals. And that really provides you a robust data set to start and model extent of an ore body. So at that site, you'd have rare earth elements, germanium, gallium, scandium, some of the other things of interest, and you'd start to associate those in a specific location. In terms of taking those numbers and generating an economic forecast, that's quite honestly a big and brave step. So that requires a significant amount of data. You need both an average and a modal distribution of those elements of interest within a fairly well-constrained grid across your mine sites. So I was not party to that at the Brook site, but to achieve an economic number, you have to produce a lot of samples. I know they did produce a lot of samples. That's really the hurdle we face in a lot of locations with these coal-based resources. Green River Basin, for example, we hadn't done much work there until CORCM started. So we only have 3 or 4 years of understanding there. It's very preliminary. We do have locations in Powder River Basin. We've worked for a decade there, including CORCM, where we're beginning to approach sample density and statistical relevance in the data set to make those predictions economically. But it's a big step, honestly.
Right. And, we had done very little in the Gulf Coast also. I mean, and so we were probably more like your Green River, Wind River project. We just started with the Department of Energy Core CM program. And so we have limited data, whereas I guess you guys at the Powder River Basin and then Nolan, Faker and others in North Dakota have a much longer track record and a lot more data to develop an understanding of the distribution of rare earths and other critical minerals. So, Davin, I first became aware of your work with the coal ash, and since the Powder River Basin, supplies about 40% of U.S. coal and exports it to many other regions. So Powder River Basin coal ash is all over the U.S. So there's a lot of interest in understanding what is the potential for extracting rare earths from coal ash deposits. So can you describe your work with the coal ash then in the Powder River Basin?
Yeah, I can do that and provide a quick summary of how I got here. This is actually what first landed me a job here at School of Energy Resources. So I completed graduate school. I studied granite, again, where some of the traditional rare earth elements occurrences are. I studied uranium provenance minerals. That expertise lent me to a job here where they were beginning to survey power station waste or rare earth elements. So this is 10 years ago. I actually had very little expectation to find anything interesting, but it was a great opportunity to apply my skills. And we did. We began to survey power station waste across the state of Wyoming. So Green River Basin, Powder River Basin, two different coal systems provided great contrast. And sure enough, a very interesting result occurred. We noticed vast differences in the chemistry and in some locations in the Powder River Basin, some nuanced differences in the rare earth element concentrations that suggested the coal systems themselves need to be looked at. So we expanded that work with assistance from National Energy Technology Lab. We really provided some assistance to them in starting to expand this look at coal. But it really does tie back to that original glance at the power station waste. And to this day, we've continued to survey those materials, tie them back to the feedstock coals. And now in support of National Energy Technology Lab, there's a pilot facility that was being stood up in the Powder River Basin to utilize those waste streams from power stations locally.
Right. And as I recall from your one of your papers in Renewable and Sustainable Energy Resources, the coal ash, the average concentration may be around 300 parts per million in the coal ash. And so one aspect, of course, is the concentration. And so the concentration of rare earths, the average concentration in continental crust is about 180 parts per million. And but then the other aspect that you mentioned is how readily extractable are the rare earths? How easy is it to extract the rare earths? And so your finding then from the working with the coal ash is that the extractability was pretty high. Can you talk about that a little bit?
Yes, absolutely. And that was something early on we realized here at School of Energy Resources. And at the same time, luckily, some very smart people were realizing this at National Energy Technology Lab and elsewhere. There are other references, but calcic materials are famous in the geologic record for readily weathering. And we began to see, while we were surveying older landfills of ash of the calcic Powder River Basin materials, that it seemed like some of the rare earth elements were mobilizing or more readily weathered in those materials when we were comparing to landfill materials in Green River Basin. Those materials lack calcium, and they are silica and aluminum rich. So the silica aluminum bond in nature is traditionally very difficult. They are very happy together. It's very expensive to break that bond. In the Powder River Basin, the calcium content is high enough that it's really mimicking natural systems, high calcium systems in nature where things weather more readily. So that was kind of a first guess. colleagues at National Energy Technology Lab noticed this in 2019. Dr. Mengling Stuckman, Christina Lapano wrote a paper. We went to that same conference and kind of looked at each other like, hey, we have a similar idea here. Realizing that because of the calcium, the glass that makes the fly ash is much more susceptible to chemical weathering, or in this case, acid extraction. I'm sure there's other chemicals you could use, but it's much easier to extract from. So there's a paper we all reference, Taggart et al. He had done some preliminary testing on a variety of fly ashes nationwide, and he had found the same thing, that although the concentration is lower in Powder River Basin fly ash, the extractability percent is higher because of that calcic nature. So that was a happy coincidence as well.
Right, right. And so in that Taggart paper, he had a fly ash, or he had ash samples from the Appalachian coals and from the Illinois coals, and then also the Powder River Basin. And so the concentrations, total rare earths, may be about 500, 550 parts per million in the Appalachian, and 480 or something from Illinois, and then 300 and something from Powder River. But the extractability, the Appalachian coal's most silicic material, and so more difficult to extract, maybe 30% extractability relative to 70% extractability from Powder River in that paper. And so you mentioned that you've been working some more on these, and you have the extractability to be even higher.
Right, and so that's important. Those first tests, it was the same method for each fly ash, which is a great place to start. You have control, and you had around 30% extraction in those silicic, high silica materials. Powder River Basin, again, where we have calcium, that initial result was around 70%. In some of the testing to scale up, where we're considering how to deal with calcium, its reactivity with different acids, we're achieving over 80, over 90%. And some of the really, really well-conducted tests I'm aware of are over 98%. So I think it's a lesson for, not just the process that has been developed for Powder River Basin, but any extractive process. It's always step by step, and you begin to tweak that extraction to the material's specific elemental needs. So it was a few years to get there, but it is very promising now. It's a good high percentage for the extraction of total rare earths, despite it being a relatively low concentration in terms of feedstock.
And part of the reason it took me a while to grasp this, part of the reason it's a low concentration, is that the rare earths are at the margins of the coal seam, and you've got the whole coal that you've burned, But if you were really trying to target for rare earths, if you focused on the margins, you might get a much higher concentration eventually. And so, that's extremely interesting. But, one of the things, talking to Nolan Thaker in North Dakota, they limit their extraction. The bench scale project suggested maybe 70% extractability, or even higher. But because of uranium in the coal, they don't want to create a waste stream that is hazardous. And so they probably limited to about 50% extraction to avoid having an overly concentrated waste stream with radioactive materials like uranium and thorium. Does that factor into your work, or, how does that?
Yes, and this is very much worth talking about. The co-production that can benefit an extraction process can also be very detrimental. And uranium, the radionuclides are expensive to get rid of. A lot of regulation and policy permitting considerations there. In the Powder River Basin, uranium thorium concentrations are anomalously very low. That was also a surprise. Some of the Green River Basin materials have uranium and thorium in higher concentration, but in the Powder River Basin, we just don't see them in high concentration. And the reason that's strange, Wyoming is also host to the largest uranium production in the United States. So we have the largest coal mines in the Powder River Basin, and we also have a large amount of uranium, and they are independent of each other in terms of element behaviors in the basin. And that's part of what we're working on as geologists, trying to understand why these coals are so high in some metals and not in uranium thorium. And as a prospecting tool, which sites have the lowest concentrations of uranium and thorium so that we can target those for critical minerals production and not have that burden, not have that excess burden on the process.
One thing that I really liked about your rare earth elements in coal ash paper was the technoeconomic analysis that you did with it, and highlighting the importance of these co-products, and emphasizing that it is essential to have co-products. I mean, I think I was reading the other day, maybe Powder River Basin coal sells for maybe, $15 a ton, I'm not sure. But then when you export it to other places in the US, that price can go up to $30 a ton because of the cost of transporting the coal to the other regions. But can you describe a little bit the technoeconomic analysis that you did on the coal ash?
I can. And let me first say, I won't take credit for that chapter of the paper. Those are valued colleagues at Center for Business Economic Analysis who are much, much better at making those calculations. But the two hurdles recognized, and that paper is, I would say, dated a few years now. Hopefully we can all work together and come up with a new version of this. But one of the hurdles was technology. Technology hadn't advanced far enough along to make calculations on commercialization for extraction from rare earth. We're getting closer there. And the other was exactly that, transportation costs. So if we are able to co-associate extraction facilities close to where these waste streams are produced, we have significant economic advantage. That being said, there is this idea, all these trains leave Wyoming full of coal and they come back empty. They are servicing a fleet of power stations nationwide that are producing fly ash. And there is some consideration of what does that look like in terms of economics forecasting to bring those materials back to a central facility for processing. But initially, I think those findings of co-association are probably more relevant today until a lot more work is done.
And what percentage of the ash is fly ash and what percentage is bottom ash? I know most of your work focused on the fly ash because it's finer grain, maybe more uniform. Can you talk about that a little bit?
It's generally an 80-20 cutoff. So majority is fly ash. The bottom ash is heavier. It does tend to have greater concentrations of rare earths and critical minerals, the slag, the glass, but it is a lesser percentage of the material. That being said, there are some upfront processes being considered to preliminarily crush it or provide us with a more accessible surface area of the material. We did a lot of studies on that and found it's growing minerals. It looks like an igneous system. They're very cool thin sections as a geologist to look at. We see pyroxenes and things growing, feldspars. So it's a living geologic material we're making. But because of that, it would require some upfront processing to make it viable.
Right. And you mentioned, and also the folks in North Dakota emphasize the importance of co-products. So, I mean, I hear about bricks, roof tiles, humic acid for soil amendments, activated carbon, graphite, graphene, all of these different potential products. So I think you have a separate group that's working on that. Is that correct?
We do. We have a center here at School of Energy Resources focused on carbon utilization, manipulation. It's a lot of engineers over there, very smart people. One thing we have with Powder River Basin is very high volumes of coal. As you stated earlier, we're supplying 40 to 46% of the U.S. coal stock comes from Powder River Basin. So the solutions there we seek for co-production include a lot of high volume carbon materials. There are soil amendments, building materials, a lot of high volume carbon materials. Often those solutions are considered low value, but we are exploring high value, high volume carbon uses for those materials. In contrast, some of the coals in Green River Basin are apparently much better suited. They have much higher carbon contents than Powder River Basin, so they're much better suited for advanced carbon materials, those lower volume, much higher value carbon chains. So we're looking at co-production in both locations. It is an important consideration. I know that the folks up in North Dakota are looking at humic acid, as you said, and other co-productions. It really is the economic hurdle, using the entire material. And the more you can diversify that, I think the better off many of these projects will be.
Right. And the Department of Energy program, the Core CM program, started off focusing almost exclusively on coal, carbon, or coal material and coal ash, and turning waste into resources, which is very valuable. But then they expanded the program halfway through and said we could look at other materials. And so you have been looking at some other materials, and maybe if phase 2 gets off the ground, we'll have more opportunity to look at these other materials. Can you describe some of these other potential materials in Wyoming?
Yes, and I agree with you. Maybe, hopefully soon, we get Core CM phase 2 off the ground for all of us. So Wyoming we are a production state, an extraction production state. We have trona in abundance, the world's largest producer of trona. So we've done, at least in Core CM phase 1, started to look at sediments co-associated with trona, trying to apply some of the methods from coal in those materials. We have heavy mineral sands. We have phosphates. Phosphatic rocks are the example geologists think of for rare earth occurrences. So we have facilities here that produce fertilizer from those rocks, so we're interested in those waste streams. Again, we are the largest producer for uranium in the country, so co-association of other critical minerals with uranium is interesting. We're trying to forward several projects there. We have mine tailings, hard rock deposits for traditional things, gold, copper. So we're looking at those materials. Zeolites, a colleague of mine, Bob Gregory, did an extensive survey of zeolites in Wyoming a few years ago, and we're utilizing that knowledge to look at co-association of a wide variety of critical minerals there. Waste streams for all those industries are being considered. Produced waters, as you're very familiar with. So not just the primary geologic material, but waste streams of those industrial processes are being considered as well.
And it always looks pretty bleak at the beginning of a study. You just think, oh my gosh, like you said earlier, you didn't hold much hope when you started to look at coal ash initially, coming from your igneous background and ore deposits. But it's amazing when we get more and more data, how much we learn, and also that it becomes more feasible, and we develop approaches maybe to coal beneficiation, or to work with the material and improve and optimize the processing and understand what's controlling where it is occurring. So it blows my mind, really. We've come a long way in the past. You guys have been doing it for over a decade, but we've only been doing it for a few years. But we've learned a lot.
We have. It's exciting. It's also daunting. At one of our annual meetings, where we all get together, I think it was presented that these projects are sort of like a new Manhattan project, and then that was quickly dismissed because it's more like our moonshot in a way. Standing up domestic supply chains of critical minerals is a significant task. So there are, as your group and the group here at University of Wyoming, North Dakota, across the country, it's a relief that some of the best minds are working on this. There are a lot of us. these collaborations we have with your group, especially all across the country, are extremely valuable. Taking lessons learned, successes, failures that each of our groups have experienced in this process. It's hugely beneficial. And I think it's going to result in some really fantastic things, a really diverse supply chain. It would be foolish to put all our eggs in one basket in this country with a single source. So this provides us a pathway that's very diverse. And it's incredible to meet with the engineers, the chemical engineers, those advancing the technologies for the extraction and separation. It's pretty amazing what they've done so far. So,
yeah, and you recently spoke with Chris Young, I think, at Element USA, and they are very interested in looking at a variety of feedstocks and trying to get it to the next level, and also working with people that would process the different elements. And Nolan Thaker has been talking to Rare Earth Salts in Nebraska, they would provide the oxides and mixed oxides. And then rare earth salts would separate out some of the different elements and other critical minerals. So we not only have to develop the feedstocks, but we also have to advance the processing that's going to be critical too in the U.S.
Yes, and I'm glad you mentioned Elements USA, among others, public-private partnerships. What we develop with private sector input is absolutely essential to make this happen. I think that's dead on. I had lost a thought there, but I was thinking about those broader collaborations that you just touched on. Each region, that's the thought there. Each region is going to produce different strengths and different weaknesses. Just the two projects we had at the University of Wyoming, Powder River Basin and Green River Basin, well, we conceptualize how to advance technologies in each of those regions. They're very different from each other. One's going to solve one problem in the supply chain, another will be something completely different. So I think that's important to keep in mind. The upfront side of this too, new ways to just access these materials. It's not just separation, extraction, and those processes we traditionally think of. A big metal building with pipes doing the work for us, but how we access those materials that are in the ground, we have to advance some things there as well. I know a lot of people are thinking about how to do that.
Right, and understanding in some of your situations in like the Brook mine, that if the rare earths are near the margins, then maybe the extraction will focus on the margins for that aspect, and maybe focus on the codes for non-thermal purposes or activated carbon or other things. So we're developing a lot of different products. And then I think you mentioned that as you process them, maybe for rare earths or critical minerals, then they may be better for other products also, what you're left with after that processing. So, and I think Nolan Thaker has seen some of the same things in North Dakota. The coal, after you remove the ash and some of the ash, then it's stronger and better for different purposes.
Yeah, absolutely. And we have a number of miners we work with who are pretty excited on this. They have not immediately offered, but suggested that they would like to go out and test some of these new mining techniques. What does a coal mine look like if it's a split stream mine where you're producing material for carbon and producing one for critical minerals, and you're also supplying a power station, which is the original purpose, of course. So a lot of the stakeholders are interested as well on how to test some of these ideas.
All right. Well, thank you so much, Davin. I really appreciate your time and really enjoy collaborating with you. Our guest today is Davin Bagdonas, who is a senior research professional at the University of Wyoming. And if you want to learn more, there will be a script attached to this podcast on the website, and also highlights and links to papers and reports to provide information on the data. So thanks a lot.
Thank you, Bridget. I look forward to all our future work on this.